Okay guys, let's take a look at today's lesson. We're looking at local linear approximations. Now, this is actually a really big deal, local linear approximations. By, later on as the year goes on, many students forget about this completely, and it is going to be, it pops up all the time. So what is a local linear approximation? Basically, it's using the tangent line to approximate a function value. That's all it is. We see that, local linear approximation, linearize, all those words, very confusing words, but it stands for something very simple. You're using a tangent line to approximate a function value, period. That's all it is. So one thing that lends to the confusion is the formula itself. If you look at it, it looks really confusing, right? That looks crazy. But to be honest, it's just that. In fact, on a formula quiz, if I ask you for the local linear formula, you can just give me this. It's just the equation of the line. That's all it is. Y minus y1 equals m times x minus x1. It's just a tangent line. It is just a tangent line at a particular location. That's all we're doing. So we're finding the tangent line at a particular location, and we're going to use it to approximate a function value. Okay, so we have a couple of different examples to illustrate this. Let's look at the first one. So we have, it says, telling us exactly what to do. Use the tangent line at 1, 3 to approximate f of 1.1. Okay, so we know how to write tangent lines. We've done that before. So let's do that. We're going to need the derivative, right, to get our slope. So f prime of x is going to be negative 3x squared. Okay, I need to do the tangent line at this particular point, 1, 3. So I'm going to sub in a 1. So f prime of 1 gives me negative 3. Okay, luckily, very nicely, they gave us the y value, so I don't have to search for it. If I needed the y value, where would I need to go? I would need to go back here, right? That's what we always do to get the y value for our tangent line. So here we go. Let's write it. So we have y minus 3 equals negative 3 times x minus 1. Now, I'm going to move the 3 over because that's what they do. So y equals 3 minus 3 times x minus 1. If you look at this and you look at this, that is the exact same thing. It's just a tangent line. Okay, now I'm going to use it to approximate f of 1.1. So the 1.1 is the x value, right? That's the x value that I'm looking for. So let's do that. So y equals 3 minus 3 times 1.1 minus 1. So we work that out. We know 1.1 minus 1 is 0.1. Of course, I like fractions, so that's 1/10. So we get 27 tenths. If you like decimals, you can put it as a decimal. That's fine. Decimal would be, what, 2.7. Either one of those. So there is our approximation. Now, once we find our approximation, we're going to work on error. That's really an important concept for us, is error. And I want to, you would have a calculator for this part. What is the error in our approximation? So what would we do? Well, we would find the actual f of 1.1. We would actually plug in 1.1 here using our calculator. Okay, I did that. So we get the actual value is 2.669. And you will need your calculator for this lesson for the finding error. So we compare our real value, which is 2.669, to our approximation, which is 2.7, and we're asked, what is the error? So logically, let's think about this for a minute. Logically, if you were asked what was the error, what would you do? How would you find the error? You would just subtract them, right? That's all you do, right? We just subtract. So we do 2.7 minus, so our error. Now, error is always positive, so it's an absolute value, so it doesn't matter which one you subtract. If you get a negative answer, don't use the negative, right? Error is just a number. It's a value. So we subtract it and we get an error of 0.031. That's our error in our approximation. Okay, so we think, well, that's okay. We're accurate to the tenths place is accurate, but once we get to the hundredths place, we start getting off. So it's an okay approximation. Let's talk about the approximation. If I have a curve and I have a tangent line here, what do you think happens to my approximation? So I'm approximating the curve, right? The farther I get away from the point of tangency, what do you think happens to my approximation using a linear approximation? It gets worse, right? It gets worse and worse. The farther away we are from the actual value. So that's something to keep in mind as we're doing approximations, that you have a better approximation the closer you are to the point of tangency. Okay, so that's just kind of a concept there. So the very first problem, we just were told exactly basically what to do. Are we okay with that? The second problem, we are told use the appropriate local linear approximation. Appropriate, now they're making us pick. We've got to pick what would the appropriate local linear approximation be to estimate this. So our task is to figure out what function are we going to use and what is our x naught going to be. That's up to us. Now keep in mind that we would not have a calculator. That's why they're asking us to do an approximation, is because we wouldn't have a calculator. Well, that looks like just square root of x. That seems like that should be our function. That would be the most appropriate function to use. Now we want to pick x naught. X naught is simply our x value of tangency. We want to pick that so that it's kind of close to 65, but we want it to be doable, right? We want it to be able to actually calculate it without a calculator. So it seems to me 64 would be our best choice, right? We would want to choose the closest best choice. So that's what we came up with that. They told us to pick it, so it's our job to pick. So we picked the equation, we picked the x naught. Now it's our job to write our tangent line. Okay, we write our tangent line. So what do we need? Well, we need the derivative, right? So we need y prime is 1/2 x to the negative 1/2. I just took the derivative of, we recall, square root of x is x to the 1/2. I just did the power rule. I'm going to rewrite it because I'm going to use it. Just helps me. Do you have to? No. This just kind of helps me visualize what's going on. I mean, that's what I'm using to generate numbers. Okay, this is my derivative, but I don't want the actual derivative. I want the derivative at 64. Yeah.
Why is the derivative negative?
Oh, it shouldn't be. It's positive. Yeah, it's positive. So here we go. I want it at 64. I need it at 64. So I put in a 64. Square root of 64 would be 8, right? And 1 over 2 times 8. So our slope is 1/16. Okay, so we got our slope. We have our x value. We need our y value. Where are we going to go? Original function. Back to the original function. So I'm going here to find my y value. So the square root of 64 we know is 8. So here we go. So we have y minus 8 equals 1/16 times x minus 64. This is the vehicle we will use to make our approximation, that tangent line. Okay, so see, we really didn't do anything much different than the first problem, except we were responsible with coming up with the equation. All right, so now what do? We actually are going to do the approximation. I'm going to write it up here so you can see it just a little bit better. So we have y equals 8. We move the 8 over, right? 8 plus 1/16 times 65 minus 64. Okay, why am I using 65? Because that's what I'm approximating. Okay, so 65 minus 64 is 1. So basically y is 8 and 1/16. Or, and we're getting ready to look at error, so I'm going to look at the decimal. So the decimal would be 8.0625. So this is our estimate for square root of 65. So this is approximately square root of 65. Now let's deal with the error. Okay, so we need to find actual, so we get our calculators out. What's the real value of the square root of 65? So we put that in our calculator. and we get square root of 65 is, of course, it's a repeating decimal, so we're just going to have to kind of chop it off. 8.06225. Now I get asked all the time, what do I round to? Well, when we're looking at error, you can't round to the thousands. That's not going to help. You just have to put a lot of, place values on here, because we're comparing this number to this number. Wow, this is a much closer estimate, wasn't it? It's a much nicer estimate. So what do we do to find the error? We subtract them. We're going to subtract them. So let's take those numbers. We have our calculators. We're going to subtract them. And we're going to get that the error on this particular one is 0.000, oh that's nice, 242. So just as a rule of thumb, what I do is to determine how many place values to go. So our error is much better. It's much better than this one, isn't it? It's a much closer estimate. So what I typically do is I'll write however many zeros there are, and then I put 3 non-zero numbers, like 242 or whatever it is. That's what I do to figure out how many places to go. Because sometimes your estimate's going to be great. You're going to be like 4 or 5 zeros out. Well, we don't want to say the error is 0 because that's not true. So we want to just, keep going, write a few non-zero numbers after the zeros. And that is local linear approximation. How are we with that concept? Okay. The other concept that we are covering, which is related to this, is differentials, which is a bit more abstract, a bit more intense. So let me get to that lesson. That's on the second slide.